how do we know which projects are project worthy and which projects are maybe, not so great? So on my webpage, if you click on syllabus, you will actually see a list of criteria for the projects. They're called Heilmeyer's criteria. So, okay, I'll just write the name out and so you can look him up in Wikipedia. Okay. So this guy used to be one of the basically big influence wielders, at least I've supposedly heard, at DARPA. And basically he was in charge of helping to decide who to give money. And so at some point he probably in that process got a little bit frustrated, or maybe at some point he just explicitly formalized it, and he came up with a set of 5-6 questions that he should be able to answer for, in that case, the projects that people proposed. And these were very common sense questions, such as, well, why is it different? But what is new? Why is what you're doing better? How can you falsify? Basically, how can you measure if that you failed or succeeded? So this is also important. Now, that type of questions, while sounding moderately old-fashioned, are actually questions that are incredibly useful if you are trying to pitch for funding, or you're writing a grant proposal, or also if you're writing a paper. If you write a paper and somebody goes and reviews it, you need to convince them that this is a paper that actually should be published. So you need to address what is different, what is new, what is better. Why is this paper better than everything else that came before? And to some extent, go through those questions when you think about a project and try to see whether you will be able to answer them in a meaningful way. Now, projects, since this is research, don't mean that they all have to succeed. Right? Sometimes you build stuff and it doesn't work. That's an insight. Unfortunately, there are very few journals of negative results, and I must really say this is unfortunate. Sometimes people do publish them, and this is, I think, a really useful thing to do. But the bottom line being, if you try something and it doesn't work, and you can show that you actually did a good job at trying various things out and were methodical about it, this is going to be a good project. So, you shouldn't necessarily propose something just because you're absolutely sure this is going to work, because this leads to very boring things. Of course it's better if it works, sure. That's clear. If something works, then maybe you can actually write something up and tell people about it. But you don't necessarily have to play it safe as long as you make a good effort. So you can get an A for effort. Okay, good. So given that it's already reasonably late today, I'm going to very briefly go over peer-to-peer networks and then start talking about computation scenarios. So I don't want to spend more than 1 week next time on systems parts. So peer-to-peer networks, I'll just very quickly tell you what they do, and then I'm going to not talk about how they build them. So the point is, and this is the thing that you always need to keep in mind, why would you want to use a peer-to-peer network? Well, the point is, you may have a very large number of highly unreliable nodes. So you probably don't care so much about peer-to-peer if you have, a computer cluster and it has a decent uptime. And you want to be able to find these objects in that large set of nodes in logarithmic time. It's an overlay network. In other words, it does not supplant or replace any cabling and TCP/IP things that you might have going on anyway. It's a network that sits on top of all of this to route things around. So Joe Hellerstein, for instance, would be probably the guy from whom to take a class if you'd like to know a lot more about overlay networks. I don't know whether he's teaching a class right now, but he would be the guy to talk to. Anyway, so the key idea again is you use this distributed hash table to decide where to store an object, except that you don't even know whether that machine exists. Now what you basically do in order to store things is you have an object that you want to store, you compute its key, and then you say, well, find me the machine with the machine ID nearest to that key. And then essentially all of the magic that happens in peer-to-peer is this very efficient search procedure, which will in the end find you the machine that is closest to the key. And so pastry, this is what's going to be described in the next few slides and we're going to skip over it, is one such mechanism, and there are a few others. And well, you can use that for things like publish-subscribe systems, load distribution and caching, similar to what I mentioned before, or in general distributed object storage. And I'm going to leave it at that in terms of peer-to-peer. If you are interested in that, I mean, do read that paper by Rostrom and Druschel. It's actually a very nice paper to read. It's very clearly explained. So there's a lot of system stuff that I did not talk about. So gossip protocols, for instance, actually have very nice connections to machine learning. There are all those issues about time synchronization in quorums. So there are, for instance, two implementation, Google Chubby and Yahoo Zookeeper, which implement those Byzantine fault tolerance things. And there are issues about serialization, and you may have heard of JSON, you may have heard of Thrift, protocol buffers possibly, or Avro. So these are ways on, if I have records, I write them to disk, or send them over the network. You may have heard about XML, which is a rather horrific way of serializing data. But okay. And then there are all the issues of how do I actually get machines to talk to each other, and that is an entire engineering can of worms in its own, right? So MPI, I would probably not use it if I don't have to. OpenMP may be a good idea if you have a very nicely homogeneous cluster. This is a beautiful inter-process communications system. ICE, it's actually all open source, GPL, and so on. So look for a website called zeroc.com. The good thing relative to MPI is that it deals with a lot of the mess of having to worry about threads and how you send messages along and make sure that they arrive and all that fairly automatically, and does aggregation, and basically it's a lot more fault tolerant than MPI ever was. So that way, so one of our engineers surprised me by, I thought it was going to take 2 weeks for some client server application, and he wrote it in 2-3 days, and it was a few hundred lines of code. So you can do amazing things with that. Okay. Now we're going to go into the actual deep end of, in terms of storage, computation, and so on. We'll do, basically Google file system, MapReduce, and all that. So let's start with the classical way how you would actually go and store data. So who of you has built a RAID array at some point? Okay, it's a few of you. I actually assumed it would be more than that. Okay, so a RAID array is a really nice idea. So redundant array of inexpensive disks, that's what it stands for, if you have up to, let's say, a dozen disks that you stuff into a single machine. So suppose I have, in disks, and I, somehow distribute my data on those disks, then the more disks I get, the less reliable my file system becomes. Because I can span the file system over all the disks, but if a single disk goes down, I basically lose everything. So I'm screwed. So what you then can do is, you can say, well, look, the simplest way is I just mirror disks. I can do that, right? That's called RAID 1. So the striping is RAID 0. RAID 1 is you mirror those disks, you get fairly mediocre bandwidth, right? Because basically I have to write everything twice. But I get fairly decent fault tolerance. At least if I lose a disk, I have another disk backup. That's okay. Now, even better is I could actually, and this is called RAID 5, I stripe the data with one disk for parity. So if I have, let's say, 4 disks, I take 3 disks to store, 3-bit, and the 4th disk stores the parity of the first 3 disks. So if I lose one of the disks, I can still use the remainder. And actually, if you think about it, this is simply an error-correcting code, albeit a very primitive one. Now, apparently, it's taken a long time for people in the disk world to realize there's an error-correcting code. So apparently, cutting edge seems to be right now that people are starting to build systems where they use error-correcting codes here. Right. So it's just because it's a very different world and people never ask that question. But the big issue, of course, is if a machine dies, you're screwed. So how can we improve things? Well, I basically give up on some requirements that I generally would have from a file system. So in an internet workload, you may have bulk sequential writes. Basically, people do stuff on your website and you log it and you dump it to disk. You might also have bulk sequential reads. Like you've crawled all your web pages and now you go and process them one by one and try to find out which one is spam and what their content is. You're probably going to disallow random writes. This is the key and really ingenious thing that Gemabot, Gobioff, and Leung had in, well, I guess probably 2000 or so. So this is the Google File System paper from 2003. So the ingenious idea was to give up on one of the standard properties that your typical file system would have. And in doing this, they managed to actually build something that scales very well. They maintain high bandwidth requirements per file. So sometimes, if I am serving some content, I might actually need a lot of copies that I need to serve. And I want to have high availability and replication. In other words, I want to make sure that I will never ever lose a user's emails or that I don't lose parts of my web page crawl and so on. So there are distributed file systems that you could use, and here are some which I would say are maybe non-starters. So those cluster versions are basically high bandwidth, they aggregate things, they work very well if you have a highly reliable system. They don't necessarily replicate outside racks, so if a rack goes down, well, you're done. And NFS, AFS, and so on, they don't really parallelize very much. I'm overly generalizing here, but this is just to give you a bit of a general idea. So, Google File System, this is original from the GFS paper. So, don't worry about all the details in it. Let me give you the basic idea. The basic idea is that I have chunk servers which hold blocks of the file. And in this case, they just picked 64 megabytes per chunk. They could have picked some other number, that's what they picked. And you make copies of those chunks. So each of those chunk servers is basically a run-of-the-mill Linux box with a few disks in it. And so if I take your email, I will put it on 3 different machines in my server center. Okay. Now, the good thing is that for the replication, I write it into the first chunk server and that one then copies it on. The master in this case, so this is why I said, well, actually this entire idea of the Karger-Akamai paper, Karger et al. Akamai paper took a long time to percolate. It still has a single master. GFS2 apparently doesn't have a single master, but only Google employees know how it's built. At least I would not know. So there, if I want to write a file, I talk to the master and ask, where can I write it? The master decides, okay, well, these machines have some, storage available, so it writes into these machines. It then does the replication and everything's fine. To read, I need to say, well, I want to get this specific file the GFS master looks it up in its namespace, where it sits, and it then directs the client to read directly from the chunk servers. So in other words, the master stores all the metadata, but no actual data. And everything that requires a lot of bandwidth, namely the chunk servers, just get hit directly by the clients. So here's an example. Client requests a chunk from the master. Well, the master actually responds with that location, and the client actually goes and writes the replica, and then the primary replica gets copied and so on. So I'm going to spare you all the details. The bad thing is it has a single master. The good thing is it actually uses checksumming. So this way each chunk server can on its own check whether it actually has the data alive. And then the master will also do a little bit of balancing. So I'm not going to go into a lot of details here because I'm going to show you something a lot more beautiful. So this is something done by a guy called Sage Weil. So who of you is using DreamHost? Okay, nobody. Okay. Anyway, so DreamHost is one of those web hosting services providers. This guy apparently seems to have made his fortune with that. Then he decided to do his PhD in Santa Cruz, and he's now building this distributed file system. It's freely available here. So here's how it works. Let's for the moment assume that all my storage machine, storage servers have the same capability. Then what I can do is I can just use this consistent hashing. So I take k out of m. If I want to have a replication of 3, I can take 3 out of m. And this way, the master actually never needs to decide where the data is being written. That's up to my hashing algorithm. And then all I need to do is I need to tell the master, by the way, I wrote a file there. Now the good thing is that I can actually then come up with interesting replication mechanisms also for the metadata cluster, and we'll talk about that later. But the good thing now is that the master doesn't actually have to decide where stuff goes. It just needs to store that you actually have the stuff. The distribution here is nicely uniform. And furthermore, if one of those machines dies, then any of the other machines is going to find out very quickly, because they occasionally go through their inventory and they check, well, are all the other copies live? And if one of the other machines isn't live, then you know exactly which parts you need to replicate. So this way, it's fault tolerant and it heals itself without the need of any central intervention. Because something that could occasionally happen is, of course, the network cables get cut here. Then even though your machines up here may still be alive, they won't be able to control anything here. So this is a very elegant way of getting proper load balancing. Now, I'm not going to discuss in a lot of detail, because it's already almost 7 o'clock, the various sampling techniques for it. Suffice it to say that even though they describe it in a systems manner, this is essentially important sampling with given load probabilities. So there might be a little bit in the assignments actually. So here's one of the cool things that you can do. You can, for instance, require that you would not like to make, well, you don't want to put all of your eggs into one basket. In other words, you want to make sure that not one rack contains all copies of a file. So you can say, well, draw from the set of racks, and basically I might want to have it in one row, but then draw from 3 different cabinets. Now within each cabinet, we'll pick a random disk. Or I could say, well, you can pick 2 from one row and 1 from another row. I can design distributions accordingly. And this is something that I can do directly through consistent hashing, so this way it's predetermined for the key of a file, where it needs to go. This then gives me interesting samples like how to add files, and I'm actually going to skip over all of that because it's, yeah, we probably don't have enough time unless somebody who wants to hear about how this works. Okay, I think that's the minority.
It kind of depends on what the next thing is. So
okay, the next thing is going to be MapReduce. I think that's more important. But the key point to take home from all those distributed file systems is that your data will be broken up into blocks. And they will live spread out over maybe 1,000, maybe 10,000 machines. Now what that means is that in many cases, the processing should rather move to where the data sits instead of moving the data to where the processes are. Simple thing, because I mean you might have, you know, a couple of gigabytes of data, but your code might only be 100 megabytes. So then it's much faster to move the code to where the data is. And what I'm going to show you next is how you can actually marry in a rather beautiful way this distributed data layout with distributed fault-tolerant processing. And the most famous example is MapReduce. And at the moment, everybody is doing MapReduce. I think MapReduce is an absolutely amazingly wonderful, ingenious idea. However, it is a really foolish thing to try to shoehorn every single algorithm into MapReduce. You can probably do it, but it's probably not going to do you much good. So, small anecdote of something that happened to me in the first week of being at Yahoo. So I wanted to parallelize a specific algorithm, LDA for that matter. And I started looking at how to parallelize it. And of course, I first started looking at Hadoop, because that's, you know, what everybody does. And it was taking me a while, and at some point I got an email from an intern who wrote me an email telling me, Alex, I parallelized this thing and it's running on Hadoop and it's good. And I felt very embarrassed because I thought, this intern beat me to the punch, you know. So I looked really silly. Anyway, so I met up with the guy as soon as I could, tried to find out what was going on. Then I asked him about performance figures. And it turned out that his code was getting slower the more machines he was running it on. Okay, so, and you could now say, okay, maybe stupid intern, he didn't know what he was doing. No, there were some systematic issues with that specific estimation problem where it's really hard to parallelize it in a MapReduce fashion. And we will see that actually in a couple of weeks down the line. And so one of the guys who actually made it work sits here, so it's Mohammed. The other one sits in Bangalore, Shravan, and a few other guys, Amr Ahmed and so on, who really made this work. So the point being, MapReduce is not necessarily the only solution to your scalability problems. So you may want to shoehorn the algorithm into MapReduce or maybe make it compatible at least on the outside, but you should keep in mind that there's a much richer slew of tools at your disposition that you can use. And this is why I essentially inflicted all the systems background upon you, to make sure that at some point when you have to solve those scalable problems, you will actually think, if you run into trouble with, let's say, MapReduce, that there are also very effective tried and tested algorithms beyond that that you can use. Okay, so with all those caveats and warnings and danger signs, so here's MapReduce. You know, you have maybe a couple of thousand faulty machines, and you have lots of jobs which are typically embarrassingly parallel, except for, you know, some small operation. And if you've done functional programming, which I haven't, but I know that much by now, you know, there are those two operations. One is called map, and the other one is reduce. And the map basically, if you've written any code in Python, you would, for instance, know it as well. Basically takes each of those key value pairs and outputs a new key value pair. Map. So for instance, one would be that I, you know, take the first and last name, and then your student ID, and then map it into student ID and last name, or student ID and first, or and number of characters, or whatever else. Reduce takes all those key value pairs and aggregates all the instances with the same key to some aggregate. And the important property of reduce is that it's commutative. So in other words, the order in which you receive the objects doesn't matter for the code, and that you can also, in many cases, reduces again. So you can, it's basically an associative property. Now, so here are two pictures, and that's directly from a nice set of slides that they did for the DOE. So you have basically a set of inputs, you have a mapping function, you get outputs, and reduce basically takes this input list and does something interesting with it. So the example that everybody brings up as the first and simplest MapReduce program is an extremely naive word count. So I'm also going to do that. So the map takes, the document ID and the document. Usually documents have some ID. And for each document, well, we do the word counts, and we admit that maybe the word that occurs 3 times, and the word and is 5 times, and the word dog occurs once. So I emit those pairs. So in other words, map actually blows up the data rather drastically. So you're going to emit a lot of key value pairs for a single input. There's no necessity to emit the same number of items. And then reduce now takes all the tuples for which, let's say, the word that is the first one, and sums over the counts. Now, how this is done in hardware is going to be explained in the next slide, but basically this will give you in the end reductions where you have the word ID and the aggregate count in your entire set of documents. And you actually need to reshuffle things a little bit. So MapReduce, what it does is, it splits the data. So this is from the original Gimmelwatt and Dean paper. So you notice this guy showing up over and over again. So the workers take this key value pair. So they didn't really explain it so much in that context yet, but so they have all this fork and assign map and all that stuff in it. But it takes the data, splits it up into chunks. Each worker gets one of them, maps those key value pairs into new data, writes it locally to a disk, to again this Google file system or Hadoop file system, and then, and it will already do possibly distribute it according to that key. Then it may reshuffle things, and then the worker, or otherwise you get the remote read, will just pull the corresponding keys that are relevant for this worker into its input feed, and then it writes that to some file. So that's MapReduce as it was originally conceived, and it's an extremely powerful paradigm. So for instance, if I want to go and compute the aggregate gradient over a large data set, well, I break up the data set into individual chunks. I compute the gradients on each subchunk. The mappers then emit those. The reducer just adds up those gradients, and then I do something interesting with it. So sometimes you need a combiner in the middle, which basically pre-aggregates keys before sending them to the reducer just to save bandwidth. Now the important thing is the mapper needs to be stateless. This is important because if it had state, then if the mapper dies and I had to restart it and it's processed some data and not the rest, then the outputs of the mapper would be different accordingly. The fault tolerance is quite nice because, I mean, first of all, you just, since you've broken up the data into individual blocks, you can just, redo the same computation maybe in a different machine with a different replica. And of course, it also moves the data to where the code is, the code to where the data is. And this works for a lot of algorithms really beautifully. So there's, for instance, this famous NIPS paper from, I think, 5 years ago that basically everything in machine learning is MapReduce. that I think made MapReduce in machine learning rather popular, but it also, I think, overgeneralized a little bit. They were very excited about it. It's a really great idea if you have an algorithm that requires a small number of iterations. Small number being like 10. Large number being like 1,000. So don't do it if you have 1,000 iterations. Do it if you have 10 or less. One issue is that the mappers, since they are stateless, lose all the context if they are reinvoked again. So then there are patches to Hadoop, for instance. Some of them are like Hadoop++ or Hadoop, which try to address it. But basically, plain vanilla MapReduce isn't suitable for it. The other bad thing is that it actually does all the communication between processes via I/O, via file I/O. So it basically does something, computes stuff, writes it to disk. Then some other process comes along, reads it from disk, and pulls it out again. If you think about, this is about the dumbest way how to do inter-process communication, right? It's about the slowest possible way that you could ever imagine. And this is exactly what MapReduce does, at least the published version and also what's in Hadoop. So there are obvious ways how to improve this, and I'm going to conclude the lecture with that because it's already 7 and I think some of you might have to catch a bus or a train or whatever. I'll stick around for a few more minutes for questions, and we'll do the last part of all of this next week.